Okay, we're going to start looking at connected particles. And to introduce this, we're going to be looking at Newton's third law, and we'll begin by thinking of objects connected by rods. So, Newton's second law is when we use the force on the system is equal to the mass times acceleration, and we can break up the components of the force acting on something and work out its acceleration. And that's what we've been doing up until now. Now we're going to add in Newton's third law. So this states that for every action there is an equal and opposite reaction. So that means that for every interaction there's a pair of forces of the same magnitude but act in different directions. So let's think about a suitcase. And we've got this person here, and they are pulling the suitcase. And this rope is under tension. So there's a force down here, but there's an equal force in this direction. And so in this system, we can, so that the force, the tension in the rope, the tension T in the rope, has an opposite, and they're both equal, but in opposite directions. Now, when two objects are in contact, each pushes on each other with an equal and opposite normal contact force. So we've got our normal contact force here when this box is just sitting on the ground at rest. That's equal to the weight. The normal contact force is equal to the weight, and this is because of Newton's third law. Now, if we were to think of our box on an incline, we've got our normal contact force, we've got our friction, and we've got our weight. It's pushing into the slope with its contact force, and the slope pushes back with an equal and opposite contact force. When we draw the force diagram, you usually show only the forces acting on the box. So here we show the normal contact force of the slope on the box. So when we think about in our force diagram, we only show the forces acting on the box. So here we've got the normal contact force of the floor acting on the box, but there's also an opposite R coming down here, but we don't put that in. But just bear this in mind as we move forward into these contact particles connected in the system. So we're going to be thinking about objects connected by rods. So a rod is anything that is modelled modelled as a rigid connector with no mass. So a rope would not be a mass, would not be a rod, sorry. Examples of this would be a car towing a caravan. So if you think about the when you connect a caravan to a car, it's a rigid system. You're not pulling the caravan by a rope, or a truck and trailer, or trains, a train with carriages. So when you've got this system, in a connected system, we can apply Newton's second to the entire system, or to the individual components. So let's consider the components of let's consider two, say, carriages, and they're connected by a rod, and we can have the tension pulling inwards. This is tension, and it pulls inwards. In some situations, when you calculate the tension in the rod, you might end up with a negative tension, and in that case, we say there's a thrust. It's pushing outwards, and this is going to be a negative tension, and it means the rod is under compression, is therefore a thrust. So we're going to look at some examples of how this actually works. So a car is towing a trailer, and it travels on a horizontal road. The car has mass 1500 kilograms, and the trailer 500 kilograms. The resistance to the motion of the car is 80 newtons, and the trailer 20 newtons. The driving force produced by the car's engine is 360 newtons. Find the tension in the tow bar. So first we're going to draw our first diagram. So we've got our car and we've got our trailer. and we've got the cars going with a driving force of 360 newtons, and we have our rod, and the whole system has a normal contact force with the weight is going to be 1500 add 500, which is 2000 G. And you've got a total resistance of the car plus the trailer of 80 plus 20 is 100 newtons. So from Newton's second law. So firstly we're going to treat the whole the complete system. We added all the forces together, the resistance and the masses. So this has been treated as one system. So if this second law is F equals m a, and the forces are, well, we've got a forward force of 360, and we've got in the opposite direction we've got 100 newtons, and that must equal 2000 times A, so A must be 0.13 meters per second squared. So now we can take this information to work out the tension in our tow bar. Now if you see here, this is our tow bar, there will be a tension along this bar, and because of Newton's third, we've got a force T in equal but in opposite directions. So for this we can split the two objects into two parts. So we will have our trailer, and this will have its own normal contact force with its weight, and we know the resistance is 20 newtons, and we've got this tension here, and the weight here is going to be 500 G. So this is our trailer, and now here's our car. So this has got our mass of 1500 G. It has the driving force of 360 newtons, and then there's a normal contact force, we'll call it R2 of the car. We have the tension T, and we have the resistance here of 80 newtons. So we can now take Newton's second law for the trailer and car separately. So for the trailer we have T, which is going in this direction, minus a 20, which is going in the opposite direction, and that must be equal to the mass 500 A. And then we've got for the car, we have the driving force, which is 360, then minus the 80 newtons for the resistance. Now this time T is opposite the direction it was for the trailer. It's in the same direction as the resistance, so it's going to be minus T, and that must be equal to the mass, which is 1500 times A. Now A is going to be the same for both of them, because A is 0.013 meters per second squared. Now we could either rearrange them and eliminate A from the equation, or just substitute it in from what we've got up here. So if we do our rearranging, we will find out that T is 85 newtons. So let's do another one. A car towing a trailer travels along the horizontal the car has mass of 1500 kilograms and the trailer has mass 500 kilograms. The resistance to motion is 80 newtons on the car and 20 newtons on the trailer. The driver applies brakes, so the driving force is replaced by a braking force of 100 newtons, opposing the forward motion. So firstly, we want to find the force in the tow bar. Then the car then descends a hill at 3 degrees to the horizontal. The resistance and braking force are unchanged. So I want to find the new tow bar force. So for part A, we're going to deal with the two components as individuals. So we're going to have the trailer first. Let's draw our force diagram for the trailer. And we've got our car. So we know that there's going to be the equal and opposite tension in the tow bar. We're going to have our normal contact force, and we'll have our weight of 500 G, and our car is, how much was the car? 1500 G, and that'll have its own R. We'll call it R2 and R1 just so we don't get confused, because those will be different. The trailer has resistance of 20 newtons, and the car has resistance of 100 newtons. Oh, it's the breaking force is 100 newtons and its resistance is 80 newtons, sorry. So, for Newton's second, we've got here minus 100, minus 80, minus 20. So we're dealing with, this is going to be if it's a full system, if they're connected. Minus 20 for the resistance on the tow bar must be equal to the mass, which will be 1500 plus 500, which is 2000 A. So A must be minus 0.1 meters per second, which makes sense because it'll be decelerating. So now we can do the equation separate for the separate components. So for the trailer we'll have T minus 20 times the mass, 500 times A, and for the car it would be minus 100 minus 80 minus T equals 1500 A, so this gives us T is equal to minus 30 newtons. Now I am going to clear that, and so we I just say tension is minus 30, therefore the force in the tow bar is a thrust of 30 newtons. So the tow bar must be under compression because the tension in the tow bar is a negative and not a positive. Just important to highlight that. So now we're going to do part B. So we've got our hill. So this is 3 degrees. Oh, that's terrible. Let's just redraw that. £3. And we have our trailer, and we have our car, and we have, it's meant to be straight down, 500 G and 1500 G, and we have R2 and we have R1, we have our tension, still have our 20 newtons resistance, we have our 80 newtons resistance, we have our T, T and T, and we have our 100, that they're 100 newtons braking force. So we draw all our we draw our force diagram. Now, for Newton's second law, F equals ma, just like what we'd have before. This time we have the component of the mass that we have to consider. So we have 1500 G sine of 3. So this is coming down, the component of the mass will come down the slope, of the weight comes down the slope, plus 500 G sine 3, so that's from the car and the trailer. And then we'll have the 100 newtons braking force up the slope, minus the 80 minus the 20 of the resistance up the slope, and that must equal the total mass, which is 2000 A. So A would be 0.423 meters per second. So this time, because we're on a slope and even though we're braking, the car is now accelerating and not decelerating. So if we deal with the car and the trailer separately, so for the trailer we'll have T, which is down here, plus the 500g sine 3, then the minus 20 must be equal to 500a, so that's the trailer, and the car will have 1500 sine times 3 minus the 100 from the braking, minus the 80 resistance, minus the tension in the tow bar, and that must equal to 1500 times A. Doing all that calculation, rearranging everything, A is equal to minus 30 newtons, which is what we have below. So in this case, the tension in the tow bar is still a thrust of 30 newtons. So let's deal with one more, which is going to be a bit more complicated. So we've got a model train. And it consists of an engine. This is like the locomotive, the actual kind of choo-choo train bit of it, if you like. So the engine is coupled to a chain of 4 trucks. The coupling between the engine and the first truck and the couplings between the other trucks can be modelled by rigid rods. The train is moving on a straight horizontal track. The engine has mass 0.8 kilograms and each truck has mass 0.2 kilograms when empty. The resistance is 0.06 newtons on the engine and 0.01 newton on each truck. So that's important to remember, it's on each truck. Let's spell that properly. There we go. The driving force of the engine is 3 newtons. A mass of 0.1 kilograms is placed in each truck. Find the tension in the couplings, and then find the tension F. So the tension in each coupling, if instead of the, if all of the 0.4 kilogram is placed in the last truck. So let's draw our first diagram to begin with. So we're going to have our 4 trucks, and then we have our engine. Each truck weighs 0.2. So each truck, the mass is equals 0.2 plus the 0.1, so it's 0.3 kilograms. So there's going to be 0.3 g down here, and because it's on a straight track, the normal contact force is going to be equal to it, so it's just going to be 3 newtons. So we can just call this 3 newtons for each truck. I'm just going to change this just to make it the same. So it's 3 newtons, okay? And so they'll all have their 3 newtons for the normal contact force. Now they have 0.01 newtons resistance, so that's the same for them all. And they have different tensions. So let's put that. So let's get this, the one for the train engine. So it's got 3 newtons driving force. This will have, the engine is mass of 8 kilograms, 0.8 kilograms. So 0.8 times 10 is going to be 8 newtons. And that'll be 8 newtons. And then there'll be T1 here, which will be equal to T1 there. And the resistance is 0.06 newtons. So here we've got T2 equal and opposite, T3 and T4 equal and opposite. So if we deal with this whole system for newtons second, F equals ma, we will have 3 newtons in that direction minus, so we've got, we're going to add all the resistance forces going in the opposite direction, so it's going to be minus all those added together. So we've got 0.06 plus 0.01 for this carriage, 0.01 for this truck, plus 0.01 for the third one, plus 0.01 for the last one. And then that's going to be equal to the mass. So the mass is 0.8 plus, now we said the mass of each truck is going to be 0.3, so it's 0.3 times 4, and that's going to be multiplied by times by A, so we will then get, working all of that out, you'll get A is equal to 1.45 meters per second squared. So now we need to do it go through each truck separately. So for the first one, we've got 3 minus 0.06 minus T1 equals to 0.8A. So T1 will be 1.78 newtons. So for our second truck, we have T1 coming in this direction minus T2 in that direction minus 0.01 in that direction, and that is going to be equal to 0.3, the mass, times A, which we've already worked out, and then you can work out, slotting T1 into here, you then get T2 is equal to 1.335 newtons. So now for the third carriage truck, we'll have T2 coming in this direction, minus T3 in that direction, minus 0.001 is equal to 0.3A. So here we get T3 is going to be equal to 0.89 newtons. So for our final truck, we'll have T4 minus T3 there's T2, T3, I'll miss this one out. So we've got so now we're on the third truck, so it's T3 minus T4 minus 0.01 equals to 0.3A, and that then gives us T4 is equal to 0.445 newtons. And that gives us a tension in all 4 of them. Now, we want to find, if we put all the mass in the last truck, how does it affect the tension in the couplings? We'll redraw our force diagram. So we've still got our 3 newtons, we've still got our 8 newtons, and our 8 newtons. We've still got our 0.06 newtons, and we've still got T1. And this time this will be 2 newtons. We've still got our resistance, and and these are T2, and this will be 2 newtons, 2 newtons, T3, and that will be 0.01, T4, this will be still 0.01, oops. And on the final, this is where it gets different. Oh, I forgot to put the 2 newtons, 2 newtons. And here we have, because of all the masses in this truck, it's going to be the mass of the fourth truck will be the mass plus the cargo together will give us a mass of 0.6, so that's going to be 6 newtons of weight, 6 newtons of normal contact force, but our resistance here is still 0.1 of a newton. So the overall, if you work out the overall system, the overall mass hasn't changed. So from Newton's second, we would still calculate that A is 1.45 meters per second squared. And this time we're going to go through the same process that we went through before and do each part separately. So for our engine, we've got 3 minus 0.06 minus T1 equals 0.8A. So T1 is 1.78 newtons. T1 minus 0.01 minus T2 equals 0.2A. And again, T2 is going to be 1.48 newtons. T2 minus 0.01 minus T3 equals 0.2A. T3 is going to be 1.18 newtons. And T3 minus 0.01 minus T4 is 0.2A. Working that out, you get T4 as 0.88 newtons. And yeah, so and you'd get on T4 minus 0.01 equals 0.6A. And you get your T4, and so you work all your different components out. It is tedious, but there you have it. So hope that helps.